So dear students, I'm back with the new lecture on biomolecules, and in this chapter we are this time understanding the carbohydrates, and in carbohydrates we are understanding the subtopic monosaccharides, and monosaccharides, or we are discussing the monosaccharides. And in previous lecture I told you about the monosaccharides are polyhydroxyaldehydes and ketones, and the monosaccharides can be divided into aldoses and ketoses accordingly. And on the basis of the number of carbon atoms, they can be trioses, tetroses, pentoses, hexoses, and heptoses. And at the same time, I gave you the example of each one. Now, today we'll take the examples of monosaccharides, and we'll be discussing their special thing. That's actually the this isomerism of the monosaccharides. In this case, I would like to first of all tell you that because we yesterday took an aldotriose. Aldotrioses are, we'll take an example of aldotriose. So as you know that all carbohydrates, they end with a suffix "-ose. So the suffix "-ose you must remember. And we are here understanding an aldotriose, that is, I would like to provide an aldotriose called a glyceraldehyde. So glyceraldehyde. So if you just glyceraldehyde is having it's having a formula C3H6 and O3. So that means it's having 3 carbons, 3 hydrogens, and but it's an aldehyde. So is or it's having a double bond here. And here this will be a configuration of an aldehyde, how it looks like. And in glyceraldehyde, we just have a configuration like this. I would like to share it with you here. So in monosaccharides, we are doing an example of this aldehyde, glyceraldehyde. So if you look at the glyceraldehyde, it is its structure is this is a glyceraldehyde. So this is a glyceraldehyde. It's having aldehyde group here, and at the same time it's having a second carbon, and to the second carbon there is OH group here on the right side, and then you're having here one H group and CH2OH group here. So this is called as glyceraldehyde. And if you look at the glyceraldehyde properly, so let's have a look at, this is the mirror. This is the mirror, and I'm just explaining this time the Fisher projection formula, that we are understanding it is mirror. And in this mirror, this is the glyceraldehyde ball model of the glyceraldehyde. And in this model, you see that this is an aldehyde group, and this is an OH group. This is a CH2OH group here, and this is the H group here. So if you look at the image here, this image is on the right side. So this is here on right side here, because it's on my right side. That's why I'm saying on the right side of OH is present on the right side. But if you see its mirror image, it's showing that it's OH is present on the left side here, and here it's OH is present on the right side. So why? Because this type of the configuration, so that means the two structures, this is same, you know, CH2OH and CHO aldehyde group is same. Let's see, but you'll see that OH here is present in the structure. OH is present on the right side, and here OH is present on left side. So OH on right side, and in another structure, its mirror image, it's having OH on left side. See clearly that it's having OH on left side here, OH group on left side. So this condition is this type of the carbon to which the 4 different types of functional groups are attach it. So look at, there are 4 functional groups. This is the main carbon atom, and this is the main carbon atom here. And to this carbon atom, 4 different functional groups are attached. And if you just draw it like this, again, I would like to draw it here, so that if we have this carbon, and here I would like to draw it. So if it's the carbon here, and there's one of the group here, it's called A, one group. Then there is another group, and another, because this is the tetrahedral carbon, and X here, Y here, and Z here. So such a type of carbon. So this type of the carbon, I will just show you to the star sign and asterisk sign. So such a type of carbon, this tetrahedral carbon, this tetrahedral carbon is linked to 4 different groups in space. And this type of carbon is called as this type of carbon. This type of carbon is known as chiral carbon. It's called chiral carbon. So chiral carbon is a very important thing. The chiral carbon is that carbon now to which the 4 different functional groups are attached. This is the chiral carbon, and here we have a chiral carbon here. And this type of, that means the chiral carbon is having a tetrahedral arrangement, and it's having A, X, Y, and Z. So 4 different groups are present in the space or spatial arrangement of these types of the groups. Now, if you look at this carefully at this structure again, that is here again, I would like to draw here. This is carbon, this chiral carbon, also called an asymmetric carbon. And here we are having 4 different types of functional groups. A, this is A, and this is X, Y, and Z. So if we place a mirror here, you place in front of it a mirror, and in this mirror, if we want to see this mirror image, the mirror image will look like, you see that this is again a chiral carbon, and this is having again A group, but here this time the Z will be here, and Y will be here, and X will be here. So that means if you look at this Z, so there is a difference in the arrangement of the groups in the space, spatial differences there. So this Z, if you see, look at there, here, the Z is present on the right side, whereas here the Z is present on left side. So that means these 2 structures, these two structures with the 4 different types of functional groups and 1 chiral carbon or 1 asymmetric carbon, these 2, they are different now. They are having the same molecular formula. They are having the same carbon, same number of carbons, same number of hydrogens, same number of oxygens. But what's the difference? There's a difference in the arrangement of the groups in a space, and making them the isomers, and such types of isomers are called as stereoisomers. They are called as stereoisomers. So the type of this type of the isomerism is called a stereoisomerism. That means stereoisomerism is the type of isomerism in which two structures differ only in the spatial arrangement of different groups around a chiral carbon or asymmetric carbon. Asymmetric carbon. So this is about, you can see the two things here are the structures, and such a types of structures are called as stereoisomers, which differ in this. And there's a special class of the stereoisomerism which is called as enantiomers. Isomers are the enantiomers. Enantiomers, what's it? When two stereo isomers or non-superimposable mirror images. Such a type of stereoisomers are called as, such types of stereoisomers are known as enantiomers. Enantiomers, these are called enantiomers. Enantiomers, when two stereoisomers are non-superimposable mirror images. Suppose if we just took at, I'll use another color, and if I take this image, and if I take this image and I will place it here on where this, suppose this is a carbon, and I'll place it on here, and this is A here, and then this is Z here, and then this is X here, and here it is Y. So the two structures do not superimpose, hence they are called as enantiomers. So, and this type of the enantiomerism is a special class of stereoisomerism in which the two isomers or two stereoisomers are non-superimposable mirror images of each other, and hence we call them as the stereoisomers. So we have now the monosaccharides, and if we take the examples, one of the example of the monosaccharides, do they follow this type of the isomerism? Let's take the simple triose. We'll take a simple triose, and this simple triose is glyceraldehyde, and this glyceraldehyde, just draw it like this, CHO, and then we'll see it here like this. This is again, this again here, carbon, and again it's linked to, here you can say, here we have OH group, and here again we have H group, and then we have again here CH2OH group, and then so if we said look at in the mirror image like this, it will be having the structure like C, and here we'll be having CHO group, aldehyde group, and here we'll be having OH group, and here we'll be having an H group, and here we'll be having CH2 OH group. So So linking this, so if we look at this here, so again, linking with this and linking with this, and here OH is present on the right side, and here OH is present on the left side. So accordingly, they will be called two non-superimposable mirror images or enantiomers. There will be stereoisomers, or we can call them as they form a pair of enantiomers. So enantiomers are the two non-superimposable mirror images of this, and the structure in which the OH is present on, when OH is present on right side, it will be called as a D glyceraldehyde, and in where the OH is present on left side, OH on left side, it's called as L-glyceraldehyde, L-glyceraldehyde. So D and L are, two. So D and L are two, D is here pronounced as D. So this will be D-glyceraldehyde, and this will be, again, this will be L-glyceraldehyde. So both are the forms of the D and L glycerides, are the two forms, two enantiomers of this. So today we'll just do this much because the file will be heavy.